continuing the discussion on infrastructure that's required for LLM to run in production. So the discussion that we did around classical ML models and how they get taken to production using either the model itself or get exposed as an API, all of that applies for LLMs as well because they are all, after all, models also. But if you hand engineer the same things that you did with classical ML, which is like, build fast API by yourself or containerize using Docker or Kubernetes, etc., you're very likely to run into specific problems which are unique to how LLMs are getting served in production. So um, one of the most important reasons one of the most important class of problems would be performance. So the resources attached to the LLMs are expensive. We know that already because GPUs are in high demand and GPUs are necessary for LLMs to run. So if you don't, for instance, run your LLMs in a way that optimizes the GPU utilization, then you're sitting on a lot of wastage. That's just one example. There are many such examples in the performance domain, which make it quite hard for manual executions or manual serving, which are hand stitched using classical ML kind of techniques, to not work as effectively. So without inference optimizers, and we'll talk about what those are, the problems can come in terms of poor performance, which is in terms of poor concurrency, high latency, or inefficient resource utilization. So, and that's where these dedicated LLM serving infrastructures come into play. One such technology or one such framework is called as VLLM, and that's an Apache open source library for fast and easy serving of LLMs. And in fact, if you look at the uh, GCP Vertex AI deploying to endpoint model or method, it uses VLLMs for serving. Most of the current LLM hosting companies also use VLLMs. It's a very popular approach. There are other competing libraries which also do the same thing, some of which are open source as well. I think Ray has one such example, Ray Serve, if I remember right. But nevertheless, the concept of LLM serving as a dedicated infrastructure is something that's unique to LLMs, which is not there in classical ML. In fact, if you compare what you would do with manual deployments, which means packaging your own containers or hosting APIs or shipping models by yourself, like what you would do with classical ML, that has a significant set of disadvantages compared to what VLLM, for instance, provides. So let's go through some of these features. So tokens is how the base architecture for LLMs are constructed. So the task of tokenization is such a common task that you want it to be done as fast as possible. In a manual deployment model, the tokenization happens outside the actual LLM call. Whereas with VLLMs, it's integrated and optimized, and that makes a huge difference in terms of latency. Batching is a manual effort, whereas automatic dynamic batching is there in VLLMs. Likewise, streaming, which is number of tokens per second that you go through, or token by token that you go through, is not supported natively in a manual deployment. You'll have to actually go through that engineering by yourself. Whereas async API is a native feature of VLLM, which means it supports streaming kind of a model. So the way streaming affects is, for instance, when you interact with ChatGPT, you'll see that its response comes word by word as though somebody is typing it. That's an example of streaming. Throughput is the volume that it goes through, which is number of tokens per second. Um, if you don't have efficient GPU utilization, obviously you're not going to go through tokenization of the prompts effectively, and therefore the throughput that you achieve is actually low. Whereas with VLLMs, the throughput is as high as it can be. Uh, Latency is in this case measured with respect to the first token. So when you type your prompt, how quickly does the response start coming back? That latency is actually very high with manual deployments because there is no key value cache. Key value cache is basically the cache that allows you to cache previously seen versions of prompts and tokens and the appropriate responses that were given by the LLM in the backend. Whereas the key value cache is a native feature of LLMs or VLLM rather, and this makes for the latency associated with repeat queries or similar pattern queries much lower. So we spoke about page KV cache. Continuous batching is great for multi-user support if you have multiple users hitting the same backend, and this requires your own queuing and threading and concurrency handling in the manual deployment model. Whereas with VLLMs, it's automatic and scalable, which means you just take that, make a copy of it in another GPU serving infrastructure, you're done, right? So it goes very well hand in hand with the distributed containerized infrastructure that you would normally associate with Kubernetes. GPU utilization, of course, itself is more efficient with VLLMs. Therefore, you're getting more bang for the buck. Multi-GPU parallelism or tensor parallelism is natively available, whereas with manual deployment, you'll have to use the appropriate packages from something like Hugging Face. Memory optimizations are better with advanced features like flash attention. Quantized models are natively supported. Obviously, it's supported with manual deployments as well because you can bring in any model of your choice. With VLLMs also, quantization is supported natively now. Chat format, like you can have different types of orchestrations, no problems. Async support is natively there, whereas with manual deployments, you'll have to go through this entire exercise of UVCon with Fast API that we did in the earlier weeks. Deployment readiness, VLLMs are natively integrated with the backend serving infrastructure, or I should say serving hardware. So it makes it very easy for you to spin up clusters of multi-GPU serving infrastructure using VLLMs. And then finally, last but not the least, scalability. It goes hand in hand with the underlying hardware as well. Auto scaling becomes a very valuable feature, especially as your LLM service requirements scale up. So long story short, LLM serving is a dedicated layer of infrastructure which is very much necessary the moment you start building serious applications which have very good traction, right? Something to keep in mind. Okay, let's talk about cost. We spoke about infrastructure as influencing cost already. Let's talk about other types of cost which also play a role. Especially in the pre-training and the fine-tuning stage, there are two major levers of cost. One, you might have an unexpected resource utilization, and that's fundamentally because of the nature of both pre-training and fine-tuning. So if you remember the fine-tuning exercise that you did in week 10, you will notice that the accelerators, the number of accelerators that Google gives you as a default, which you cannot change, is 8, which is 8 GPUs running for about 22 or 25 minutes, only for fine-tuning on an iris data set, right? The underlying model is large. Naturally, it needs that kind of an infrastructure, but it's not a joke either, right? So training can take weeks or months. Fine-tuning can take minutes or hours, and fine-tuning is repeated often. Like we saw, fine-tuning happens every week as one of the best practices. So all of this can very quickly add up with respect to resource utilization. Budget overruns can happen, scheduling delays can happen, right? And whenever these things happen, both the CPUs and GPUs as well as the human resources get bottlenecked, because human resources are also required for things like validation and verification. So the best approach obviously then is to do what's practical, which is start small and then scale up over a period of time. There's no magic to it. The second way in which cost adds up with respect to this stages of pre-training and fine-tuning is compute, right? So very quickly, you might run up a huge compute bill, especially if you use things like auto scaling, right? And also if you don't use the right serving infrastructure. So if you didn't use VLLMs, for instance, you have GPUs available with you, but you find that the GPU utilization is abysmal, right? Less than 10% for the entire month. But you still rack up new hardware setup costs because auto scaling is enabled for your Kubernetes cluster. So that's a very common scenario that you will find in large companies. So you've got to be careful about it, obviously. You've got to use the right serving infrastructure, but also use things like preemptible instances or spot instances, which control for the volume of, number of instances and the cost that's incurred. At times, it might be beneficial to also do on-prem hybrid workloads, which means run some of these models locally, especially if you've managed to quantize them and you've got a local instance available within your data center or within your private cloud. It might be cheaper to do it there because you don't need to pay anything more beyond the initial capital expenditure for that. at the usage time, like now we've gone past the fine-tuned model, we have it ready. Now we can start using it. Now at the time of usage, obviously there is cost associated with it again, right? Because even if the LLM is hosted by you, it's running on a serving infrastructure which uses resources, and it also needs appropriate amount of um, backend uh, GPUs and things like that. Or if the LLM is hosted by a third party and you keep hitting it, the tokens quickly add up, right? So either which way, there is cost associated with using LLMs, which is the inference time. How do you control for this cost? So two methods. One, I mean, rather multiple methods. One is to tweak the model itself. Now, obviously, that's a trade-off attached to it. Like the lesser you make the model size, which means you're getting rid of weights and linkages which are potentially not important, you may find that the accuracy suffers, the performance suffers. So that's a trade-off, and that trade-off is something that you'll have to make for every domain, every problem statement. But there are techniques available for you to do these trade-offs. Quantization is one example. Distillation is another example. In quantization, what happens is you go from um, a more precise representation of data to a less precise representation of data. Like for instance, 8-bit floating point representations instead of 16-bit or 32-bit. That makes for a dramatically lower size of the model. Distillation, on the other hand, is where you're building a fundamentally smaller model from an architecture perspective, ground up, which mimics the performance of a bigger model. So, if you remember the excitement around DeepSeek when it first came out, it used distillation as a way to um, achieve the same performance as OpenAI's GPT-4o, I think, if I remember right. So it's very effective at mimicking the performance of a teacher model, right? So that's what distillation can allow you to do. And usually distilled models are orders of magnitude simpler, requiring potentially much lesser number of resources. Like for instance, in DeepSeek's case, the model that they produced, which has similar performance as GPT-4o, required rather did not require the latest generation of GPUs. It was perfectly fine to run on previous generations of GPUs, which was significantly lower cost and more easily available. Okay, so that's one approach. The other approach is keep the model the same and reduce the computation that goes into the model. So if you look at your own usage of LLMs, the same query or same type of query gets asked again and again. So if you can cache the results and replay the results without having to hit the LLM in the backend, that will save tokens naturally, right? The second thing is for certain types of queries, you might not want to respond at all because those are toxic queries or queries which have a leading focus on a certain type of bias which you want to screen. In which case, there is no point in actually going to the LLM, getting the response, and then doing your screening. Instead, you just do the screening upfront. The third would be, in some cases, you can actually truncate the query or complete the response for the query based on the context window that they have asked, right? Or based on the context that they've provided directly, or based on drags. So in which case you're avoiding the cost of hitting the LLM itself completely. A third approach which is possible is offlining workloads. So here it comes down to the application design. So let's take an example. Um, let's say that you're building a bot which responds back to the user instantaneously, and the bot will keep responding with an understanding of what the current user needs are based on the current prompt. Now, let's say this is an insurance agent bot. So the bot is looking to respond back with information about claims, about policies, about what is covered, what is the hospitals which are part of the in-network coverage, etc. Notice that these responses are going to be the same broadly for most users of the bot, right? In network coverage of hospitals, maybe 10% of all queries in a day are asking for it, which is a big number, right? Whether certain pre-existing conditions are covered is also usually going to be a response that almost everybody wants to know, everybody who has access to the bot. So in these kinds of cases, instead of always hitting the LLM with a query that the user is given, you could do a semantic search, right? Which will pre-compute the set of responses which are possible and keep it in a search engine and use that as the first responder to that particular query. And then if the user is not satisfied because the context is more nuanced, then you go back and look at the actual model, right? So it's a great example of offlining. Another very good example is, let's say you're required to collect user information in the form of, let's say, KYC information. Like, so they upload their KYC cards as a PDF. Now, your workflow is such that you don't need to process that information immediately, but you can hold on to that information and then return to the user, let's say in a couple of days' time. So basically, let's say it's a brand new insurance application. Somebody goes through a chatbot for onboarding themselves. They upload the KYC, they provide all the other information, and then the chatbot says, hey, thanks for all of this. We'll get back to you in a couple of days on next steps, right? Now, in that kind of a scenario, there is no reason to process that KYC immediately. Maybe you only need to process one of those KYC documents to assess whether it's the same individual who's given their correct KYC, which is the name, matches, etc. But the rest of the documents, you don't need to process them immediately. You can actually, process them as a batch along with all the other user information that other applicants have provided. At the end of the day, in a shared GPU infrastructure, which is only spun up for that particular purpose, right? That also is an example of offlining the workload. Last but not the least is hybrid models. So here, don't, for instance, always rely upon a third-party LLM because the tokens add up. You can run a smaller version of that LLM locally, which gives the first level of answer. And then if the user is not satisfied, then you use the backend. Or you use a completely locally hosted LLM as well. So that's also a way to control for cost. Okay, so we'll take a pause here. In the next week, in the next video, we will dive deeper into some of the governance around LLMs.